Are these functions mostly unique to binary trees, or?
That's a good question. No, not entirely, but it turns out that I don't have real percentages, but I would say 95% or higher of the trees you deal with are binary trees. And so that's all you ever see. But there are general tree or n-ary tree analogs for this. The post and pre-order are the easiest ones to do, right? The pre-order would be visit the node and then all the children in order, however many there are. And post would be visit all the children, then visit me. The in order, it's like where do you stick it between the different children? And that's just kind of iffy. Depends on the situation. But we'll find out, especially next week, we'll find out that most trees that are bigger than binary, so n-ary trees, can just be binary trees. In fact, today we'll talk about n-ary trees for a little bit again, and we'll show how you can represent any n-ary tree as a binary tree.
So n-ary trees don't need to only have 2 children, you can have more children.
Right. N-ary tree can have 0 to n children. So, that's kind of the basics of the binary tree. Now we'll talk about the operations. We can test whether a binary tree is empty. This is setting us up to make a binary tree ADT. So the things we can do, we can test if it's empty. We can check the height, find out what the height is. Remember, that's the max level of any nodes. And we can get the number of nodes, and we can get the data in the binary tree root, and we can set the data in the binary tree root. We can add a new node containing given data item into the binary tree. We can remove nodes from the binary tree, a particular node. We can remove all nodes. We can get an entry. We can test if the binary tree contains it, and we can traverse in all 3 orders. So that's basically what gives us this in terms of our contract notation we've been talking about. So we have is empty, get the height, and everything. Pre-order, traversal, in order, post order. So we have all these are the different operations that our ADT, our binary ADT binary tree ADT would support. I was considering pulling up this listing. That little thing that just disappeared said the listing code had to be in the same directory as this in order for it to work, and it doesn't work. But I'll still pull it up. These links are both. See? Oh, it works. It didn't work on my computer. That's too small. So forget all that about it not working. So I have my class binary tree interface, and I have is empty, get height, and so on. I don't need to read through all these unless there was one in particular you wanted to see. By the way, this is binary tree, not binary search tree. And so in a binary tree like this, if I wanted to find an element like contains, tell me if this data is in there, how would I do that?
You actually have to traverse the tree if it isn't sorted.
I just have to traverse the whole tree and look to see if the element is in there, right? Now, how many elements are in a tree within elements? N, right? The height, we don't know what the height is. We can ask if it's a nice, full, or a well-balanced tree, then the height is log base 2 of n plus 1. But if it's not, then it could be as much as n. But it doesn't matter, because if I am searching through this tree of n elements, and it's just a regular binary tree, not a binary search tree, I have to search the whole tree. So I have to do in searches to find anything.
You should call it scaling instead of searching.
Right. So it's the same as having a list. I didn't really get any benefit from that. So binary tree is ill-suited for searching. Ill-suited as in it's not any better than a linked list. Binary search tree, however, gives us some performance benefit. Because remember, binary search tree, everything on the left is less than the node, which is less than everything on the right. So I can take advantage of that property and I can do a better search. For example, if I wanted to find Nancy, what I do is I look at the first node and I say, are you Nancy? No. Is Nancy greater than you or less than you? Greater. Since Nancy is greater than Jane, then we know it's in the right tree. So I don't have to look at that side of the tree at all. I can just look at this side of the tree. So I go to Tom, are you Nancy? No. Is Nancy less than or greater than you? Less than, so then I find Nancy.
How do you know the value of Nancy?
This is just alphabetical in this case.
It's ASCII values, but same difference.
Isn't the complexity of searching through a binary search tree the same as it would be searching through a sorted list?
How would you be searching that sort of
Using a binary search.
Yes, they would be.
Okay.
But
So like
but a binary search does not work on a linked list,
Right. Okay.
right? Because in order for binary search to work on a linked list, you have to have pointers to all the nodes, which is kind of defeats the purpose of a linked list. So if you have everything in an array, and that's a sorted list in an array, then yes, you can use a binary search on the array. And it actually is very similar to this, right? It's the same idea. But a binary search tree allows you to have infinite expandability like a linked list, but still get the binary search functionality that you would get from an array. So here is it's the same data as this, it's just spread out a little differently. If I was searching for Wendy, in this one, searching for Wendy takes 2 hops, Tom than Wendy. Here it takes 4 hops, answer Tom Wendy. And the 2 points to take from this is 1, this data could be rearranged in many different binary search trees. There's not just one representation, because this is one, and this is also a binary search tree. And some binary search trees are better than others. This one has better performance than this one. And remember, a vine can be a binary search tree. If it was Alan, Bob, Elisa, Jane, Nancy, Tom, Wendy, that would be a binary search tree as a vine. And it'd be horrible for searching. Oh, there we go. Forgot that was there. So, binary search tree, not very good. Okay, so this is binary search tree, is the binary tree. It's the same set of things. So, how's our search look? If we were to look at it in terms of code, we search the binary search tree with our target. If the BST is empty, then then the item is not found. Otherwise, if the target is equal to the item at the root, then we found the item. Otherwise, if the target is less than the data at the root, then we call search, recursive call. We call search on the left subtree with the same target. Otherwise, we know it should be the other side. We call search, again, recursive call. We call search with the right subtree with the same target. So this is a recursive binary search on a binary search tree. This is the array version, which is just same idea. It's the binary search on the array. You look in the middle, then which half do you look in, you go in the middle of that, and so on. It's the same idea. Now we're going to look at how we add items to a binary search tree. This is creating a binary search tree. So here's my binary search tree, and I want to add Frank. So first is Frank in the tree. It's not, because Frank is less than Jane, is greater than Bob, is greater than Eliza. Nope, not there. So Frank is not in the tree. That's great. So where should we add Frank?
Wherever the search terminated.
You're saying left search tree, right?
Yeah, before Bob.
Right. So
Bob in here.
So we've got some options. One is, I'll get to yours in a second. One option is we insert it here. As we just draw a circle, we put Frank there. Does that maintain the BST property?
Yeah. But it pushes the height.
Oh, yeah, you move all the other.
Right. If we actually just like cut, made space, put a circle, put Frank there. Frank is less than Jane. Bob is less than Frank. So we're still good. So it's still a BST. But it's not a great BST because we left kind of a hole in there. And that kind of behavior is going to lead to more and more holes spreading throughout our tree. And those gaps just lead to lower search performance. So, your suggestion was we should add it where the search terminated. And that makes sense. So we're going to search the tree for Frank and find it should have been here. If it would have been here, this is where it would have been. Now, it's very simple. Create a new node and add that child. If I had tried to do this up here, I would have had to, I think I can just do that just by making a couple plain changes.
Yeah.
A lot more to keep track of, though.
But
Yeah, it's a lot more to keep track of. One of the things we'll see when we talk about implementations is tree nodes don't know who their parent is.
Yeah.
It's kind of like a linked list. A single linked list doesn't know its previous. Tree nodes never know their parent.
That's sad.
Yeah, it's sad. But we've seen a lot of dysfunction already. You know, killing your kids first before you kill yourself. All that kind of stuff. So, yeah, so one of the things that would be hard to try and insert it here is since this node doesn't know its parent, you have to kind of keep track of both of these as you go along, so you know what nodes to insert it between. We don't have to do that here. When we get to Eliza, we say, Frank should be on your right. Oh, my right's empty. Okay, now we know where to put it. We just add Frank to your right. And so that makes adding it pretty easy. I don't know why we have to see this again. Do you guys need a reminder of how in-order traversal works?
Wait, what's that?
So I don't know why they put this in here the second time. All right, we're going to come back to adding and removing is the fun one a bit. First, I want to take a second to talk about efficiency, though, of these searches. So, retrieving an item, finding it, in a binary search tree. On average, it's log n. Now, how do we get this log n? Let's go back here. I'll use this one. I'm looking for Nancy. This is not Nancy, but Nancy is on the right-hand side. So what I'm actually going to do is go to the right. I am potentially throwing away half of the search space. So I'm taking all my nodes that I could be searching for, and I'm throwing half of them away. I'm cutting it in half. And then when I come here, I say, you're not Nancy, where's Nancy? Nancy's on my left. So I go here, and now what I had remaining, I'm basically throwing half of that away. I'm cutting in half. So I'm cutting it in half each time, and that, of course, is log. So doing a search, average case, is log n. Worst case is order n. And can you describe for me the worst case situation?
It's not there.
No, that's this.
Oh.
Vine. It's the vine. This is my vine. Right? Because in the vine, I'm actually not throwing away half of the problem space every time.
Linear search.
Right, it's just a linear search. So this is worst case. We don't want this And we're going to talk about strategies next week on how we can keep from having this problem. Insertion. Log in. Again, it's just the search. Use the search to find where it should be. When it's not there, you insert it. So log in. Removal is log in, believe me. We haven't got to it yet, but it will be log in. And then traversal is order in. Why can't we traverse faster than that?
So we have to go through each item and actually solve it.
Yeah, you actually do have to look at every item to look at every item. Right? And so if there are n items, it's going to take n steps to look at n items. So you're never going to get better now in terms of traversal. So to remind you though, why is log n better than n? So if I had 1 million elements, it would take me on average over 2 times to find something, 500,000 times, right? Do you remember what